So today, we are going to cover 3.1 A, B, C, and we are going to, at the very least, start on D, because all of this stuff is stuff that you did in grade 11, and we probably reviewed earlier this year. We're going to take a couple little tangents into intermolecular forces, but really, there's not a lot here that we need to spend a lot of time on until we get to 3.1D. What you guys need to get good at doing is saying yes in a loud voice so I can hear you, and no in a loud voice so I can hear you, because I'm going to say things like, do we need to do any of this? Right? And you'll be like, oh no, we know this already. And you're going to be like, no. Okay, so we're going to practice. So I'm going to count down from 3 to 1, and then you're going to say no. 3, 2, 1. No. Okay, and now we're going to come across something where you're like, oh, yeah, I don't actually remember that. And you're going to say yes, okay? 3, 2, 1. Yes. Okay? So you guys are good at that. Anytime we come across something, you're going to answer that way. So we are all aware of what electrolytes are, yes? Yes. Oh, this group did really well here. The rest of you suck. So let's try it again. 3, 2, 1. Yeah. Thank you. Okay. Are we familiar with a diagram like this one? Yeah. That was not good enough. 3, 2, 1. Yeah. Thank you. Yeah, over there you can't be chit-chatting about other things because you're focusing on this because you got to say yes or no, okay? Now, you can get ions in solutions by dissolving ionic compounds, acids, and we're going to add one in here, or bases. Can you think of a base that is not made of ions? I got a no there. See if you can find a base that is not made of ions. Find. Where would you look? Yes. NO2. NO2 is an ion. NH2 is an ion. What about NH3? Is NH3 a base? Does it look like, at first glance, does it look like it's an electrolyte? No, because it's a molecular compound, but we know that it is in fact a base, because there it is, NH3. And how does it become an electrolyte? What does it do? Say it loudly, Katie. No, that was quietly. Say it loudly, Katie. It drops an H to whom? Have a chit-chat about it, everybody. Have a chit-chat about it. How does NH3 end up giving us an electrolyte? You don't have to answer, but how many people feel like they got an idea? Okay, I got about half of you. All right, maybe 3/4. What is the NH3 going to do? Yes? It's going to donate a hydrogen to whom? Water. H2O. And we end up with NH4 plus OH minus. Okay, so you could have a base like ammonia that is an electrolyte, even though it doesn't look like one when you start looking at it. All right, next page. Salts. How do you know if you have a salt? What is a salt? Do we know what a salt is? Yes. Do we know how to recognize a salt? Yes, it's when someone punches you in the nose. That's a salt. Okay. No, yeah, thank you. A+ for you, Harshika. Chat with your neighbor. How do we recognize a salt? Yeah, we're going to have an ionic crystal lattice, an ionic lattice. How do you recognize it from the formula? Sanya? What she said? Okay, metal plus non-metal. Is that the only way to recognize it? No, there might be other things. Yes. Ammonium. And is there anything else we could have instead of a non-metal? Yeah. Or a polyatomic ion. Now, there's an exception to this. I have a compound in mind that is an ionic lattice. It starts with a metal, and it has a polyatomic ion on the end, and it is not a salt. It is an ionic lattice. It starts with a metal. It ends in a polyatomic ion, but it's not a salt. It's a different type of compound. It's a compound which we have spent a fair bit of time studying the last little while. Acid, you're on the right track. Acids are not ionic lattices, though. But you're on the right track. COOH, that's an acid. And so that's not an ionic lattice. It doesn't start with a metal either. So it's not a salt. It's not an acid. Base. Can you please tell me a base that is an ionic lattice that is a metal plus a polyatomic ion? Lithium hydroxide. LiOH. Yes? NaOH, CaOH2, bases. Ionic lattices, metal plus polyatomic ion, but they are not considered salts. They are considered bases. Yes?
Yes.
Yes. You know what? Let's not get too wound up about the things. In the acid-base unit that follows this one, you're going to have your bases that contain, like your ionic compounds, you're going to have bases that contain hydroxide. You're going to have bases that are Bronsted-Lowry bases. And then you're going to have salts. They don't contain hydroxide, but the ions are actually, could be acidic or basic, right? So we're going to, and that's in unit 5, okay? So we don't have to do that yet, okay? All right, Electrolytes can also be dissolved acids. Do we know how to recognize acids from their formula?
Yes.
That was sad, half of you. Do we know how to recognize acids from their formula?
Yes.
Thank you. How do you recognize an acid from its formula? Everybody. Starts with an H or ends in COH, our carboxylate group. Yes. Okay, so we've got starts with H or ends in COH. So the formula of an electrolyte always starts with a metal or NH4 or H, or it ends in COOH, or it is a base. Like NH3. Okay? And just to remind ourselves, NH3 accepts a proton from water and gives us ions. All right, we have a solid ionic crystal lattice. Is a solid salt an electrolyte? No, why not? Electrons are freely moving? Oh, electrolytes. The ions have to be freely moving. Yes, I just misunderstood what you were saying. So this is not an electrolyte. The ions cannot move. Are you familiar with how to write a dissociation equation? Excellent. Okay, so we're not going to spend a lot of time on that. I did get a question this morning about are there instances where our dissociation equation, we always see them with this one-way arrow. Are there instances where we have a two-way arrow? And the answer is yes. So this would be a soluble salt. But if we have a low solubility salt, let's say, for example, Ag2S, it will dissolve, but only a very little bit. What are the products of that dissociation? 2Ag plus S, 2 minus, 2Ag plus, aqueous, aqueous. Very nice. Okay, so this is our dissociation equation for a low solubility salt. And this particular equation, written the way it is, with the solid on the left and the ions on the right, is what we will use when we are working with the K, okay? So these types of equations have a K. We will use this equation with the solid on the left and the ions on the right for K, and this is my favorite K value because it is KSP, just like Karen Spence, just like my name, okay? For KSP calculations. I'm just kidding. I don't have a favorite K value. So for KSP calculations, And it really matters that the solid is always on left and that the ions are always on the right when we do this, because it means it's going to be consistent, right? If I started flipping it over, then all of a sudden the K values would be upside down. Yes? So in our data booklet on page 5, we are given a bunch of KSPs at 25 degrees Celsius for a bunch of compounds. And what we would do is for, say, barium carbonate, we would have BaCO3 solid in equilibrium with Ba2 plus CO3 2 minus. That's always the way that equation is written. And you'll notice, take a look at these values. 10 to the negative 9, 10 to the negative 10, 10 to the negative 37, right? Our largest number is 10 to the negative 5. Yeah, 10 to the negative 5. Everything else is like way smaller, right? So they're small values. These are low solubility compounds. They are not dissolving very much at all, okay? And it's always written with the solid on the left and the ions on the right so that these numbers make sense, okay? And our KSP expression, what would be our KSP expression for this reaction here? Ba2 plus times CO3 2 minus. Do you see how if we were to write it the other way around, we would like have a 1 over, and it would just be more awkward to calculate. The reason that they do it this way is because it's like, oh, look, easy calculation. We don't have to go 1 over barium carbonate. Yeah? Okay. This particular equation here, it actually gets its own name. It is called the solubility equilibrium equation. And the solubility equilibrium equation is used for KSP calculations. And because I don't like writing solubility equilibrium equation over and over and over, I call it the SEE. AP will have no idea what you're talking about if you call it the SEE, okay? But I call it the C, okay? Solubility equilibrium equation, because we refer to it so often, all right? So that's how this low solubility compounds relate to dissociation. Aqueous acids can conduct electricity because they dissociate or separate into free-floating ions. And of course, we could have our one-way arrow for a strong acid. And we could have a weak acid, which of course would have an equilibrium arrow. And we are very familiar with those. We should be really good at writing those equations because we've got a test coming up next Wednesday and our quiz tomorrow. Covalent compounds, other than acids, and Bronsted, no, NH3, which is a base. Covalent compounds generally are not electrolytes, okay? Acids are the exception. NH3 is an exception. There's other bases that are like NH3. There's like N2H5, which is a neutral compound and is a base, but you are not really responsible for knowing that. If you are given that in a question, you'll be told the base, hydrazine, N2H5 with no charge on it, you'll be like, oh, it's a base. Therefore, it must be an electrolyte and it must accept a proton, and then it will leave behind the hydroxide ion and whatever it becomes. Okay. However, all of our other covalent compounds or covalent elements are not electrolytes because they do not dissociate in water to produce ions. Instead, they simply disperse, which means the molecules stay intact, but they separate from one another. So here we have some solid iodine, I2. And you can see each little I2 molecule is in this little I2 solid crystal. What is holding the I2 to its neighboring? Intermolecular forces. What is the name of these specific intermolecular forces here? Those are our LDFs, okay? And what does LDF stand for? London dispersion forces. And you are going to try to explain to your neighbor how London dispersion forces work. Baran, how would you explain to Jaden? Because he wasn't in 11 enriched last year. Maybe you know though already. Maybe you already did it. I don't know. One happens first, the other happens second. The temporary dipole is part of the concept of London dispersion forces. Temporary dipoles create London dispersion forces. Yeah, because it's the fact that you end up with charges that they can be attracted. Yeah. Okay, so let's remind ourselves, these are nonpolar molecules, right? And so in theory, there's no positives or negatives to make them attract to each other. And molecules are always held but together by, what's that word we use for attractions between positives and negatives? Coulombic attraction. That's the word that AP loves to hear. You can say electrostatic attraction as well. There's nothing wrong with that. They could not dock you for that, but they seem to be in love with the term Coulombic attraction. So if we had, say, a helium atom, because it's our simplest one, it's got 2 protons in its nucleus and it has 2 electrons in its shell, maybe just by chance, by happenstance. Somebody used the word happenstance in my class this morning. I was so excited. I'm like, oh, happenstance. I like language. Language is fun. Say our 2 electrons end up over on the one side. Yes? Yeah. Yes. Thank you. We have now formed a slightly negative end and a slightly positive end. So this is what we call a what kind of dipole? This is a temporary dipole. Okay, the electrons all end up randomly on one side. Now, I say all. I'm going to put that in quotes because if we had any more than two, it wouldn't have to be all of them. Yes, it could just be the majority. Right? If I had 10 electrons and 8 of them ended up on one side and 2 ended up on the other, that would be enough to cause a temporary dipole. Here it's all because if they were like evenly distributed, they'd be on opposite sides. But anyway. What happens is that a neighboring molecule or atom, we have an electron randomly here and an electron randomly here. What does this temporary dipole do to the electrons in the neighboring atom? It repels them. Okay, so we get repulsion. So what's going to happen then is we are going to end up with, those are too close together. I did not mean to make them touch. Two electrons here, 2 plus, 2 electrons here. Let's make that 2 plus legible. Okay, so now we have a slightly negative end on each of them and a slightly positive end on each of them, and that negative attracts that positive. So we have a temporary dipole here. What do we call this other dipole? That is an induced dipole. It has been induced by the fact that there's a negative charge next to it. And that attractive force between the temporary dipole and the induced dipole, those are the London dispersion forces, also known as London forces, also known as dispersion forces, also known as London dispersion forces, or LDFs. If I were writing a question, if I were writing it like a response about London dispersion forces, I would probably write London dispersion forces brackets LDFs and then just go from there. Yes?
What's dipole?
What is dipole? So that would be a permanent dipole with a permanent dipole. So that would be like if you have a polar molecule with a polar molecule. Okay? So if we had in this beaker, if I had a water molecule, let's put it here, and I have another water molecule here, that is going to be dipole. That's too big of an arrow. So dipole is between permanent dipoles. You can call them dipole forces or dipole interactions or attractions. They are between polar molecules, permanent dipoles. Alrighty. Now, are there any other attractive forces between the water molecules? there are London dispersion forces, because London dispersion forces occur between everything, okay? It just so happens that in I2, it is the only IMF. So when you have nonpolar molecules, you only get LDFs. Okay. What kind of force would we have between our water molecule and our iodine? Have a chat about that. What kind of force do we have between the water molecule and the iodine? It's another one of those ones where the name says it all. So yeah, we got a dipole. The water's a dipole. So it is the, yeah, we usually put the dipole first. So we can say dipole, and then we say induced dipole. What are the chances of dipole, induced dipole forces being asked about on the AP exam? I think they're slim. Okay, but just for completeness sake, you know, if you had to come up with it, it's just one of those ones that you name. Just like ion dipole or ion induced dipole, most of them, other than London dispersion forces, are just named for what they are. Hydrogen bonds, I guess, are the other ones that don't just have a name of what the particles are. Okay, so here we have dipole, induced dipole. Iodine is more soluble in water than, say, bromine or chlorine or fluorine. Iodine is more soluble in water than the other halogen molecules. Why is that? Have a chat about that. Why is iodine more soluble in water? Anyone want to give it a go? Yes. Okay, I2 has a larger electron cloud, therefore it is able to polarize to a greater extent. It is able to polarize more. It is more polarizable. Yes, because if you have I2, you have 106 electrons. Yes, if you have fluorine, you have 18 electrons. Yeah, so the larger the electron cloud, the larger the temporary or induced dipole can be. Yes. I2 is more, and the word that we like to use is polarizable. Due to its larger electron cloud. One 106 electrons versus F2's 18 electrons. Therefore, it can form a larger temporary / induced dipole. That is also the reason why iodine is what state at room temperature? Iodine is a? Iodine is a solid at room temperature. And the one that has the halogen that has somewhat less electrons, bromine is a liquid, right? Because it does not have as strong LDFs because it has a smaller electron cloud. And then you get to chlorine, which has even fewer electrons. And it is a gas because those London dispersion forces are smaller because it is less polarizable because its electron cloud is smaller. How are we feeling about all of that? Is it coming back or is it going in the first time if we haven't ever seen it before? Yes. Okay. Thank you, Baran. Okay. So iodine molecules are neutral, so there's no free-floating particles, so they will not conduct electricity. And when you write the dispersion equation, this and this are the same. The only thing that changes is we go from the state changes to aqueous. Okay? So would we all be able to write dispersion equations? Everybody? Would we all be able to write dispersion equations?
Yes.
Thank you. I don't know what they're talking about over there. Okay. I know this morning they were all talking about biology because they all had a biology test after lunch. All right, here we have some water, which is a polar molecule. And if we put a polar molecule into an electric field, and now these don't really look like plus signs, these are supposed to look like plus signs here. Okay, so we have a positive charged metal plate over here. We have a negative charged metal plate over on the other side. And we have polar molecules in between. Will that electric field cause the polar molecules to move? Have a chat about that. Will the electric field cause the polar molecules to move? They're still having discussions. If you're wondering why we're waiting, now I'm just stretching because they're still having discussions back there. Yes, Baran. No. Anyone agree with Baran? Yes. Anyone disagree with Baran? Okay. So we got some people who agree and some people who disagree. Well, what are we going to do? Would you guys care to defend your case?
For movement, is it still considered around your molecule would be facing a certain direction, so it's still moving away?
Okay, so the way this question is phrased, they would change their orientation. So will it cause the polar to have translational movement? Do you guys know what translational movement is?
Yes.
Excellent. Translational movement is when, yes. Will the electric field cause the polar molecules to have translational movement? Oh, only 2 people knew that. Will the electric field cause the polar molecules to have translational motion? No, why not? It's being pulled equally. This negative is being attracted to this positive, so we get a pull this way. Yes? Yeah, but that would mean that all the water molecules would have to end up in the middle. Yes? Is that going to happen? No. Why not? Because there's other water molecules sticking to the walls and sticking to each other, and they would just get in the way of each other. Yeah, if there's no space for them in the middle. Yeah, what would it would be like the parting of the Red Sea, except for it would be part on this side and part on that side, and everything would be in the middle. It'd be the reverse of the parting of the Red Sea. Because they're being pulled equally in either direction. So basically what's going to happen is the particles are just going to continue moving randomly because they have random motion due to heat. Yeah? Don't think about it too hard. Okay? So we got to pull this way. We got to pull this way. Now, if you really want to talk about the forces involved, go talk to your physics teacher, because as a chemistry teacher, all I care about is that no, it does not cause translational movement, any net translational movement. Okay? It just doesn't. Alrighty? Since there is an attractive force on both ends of the water molecules, they are pulled equally in both directions when they will not move in response to an electric field. We are not going to watch the video on electrolyte versus non-electrolyte. It is just the conductivity apparatus, which you guys have already seen in person. Yes? We're not going to watch dissolving solid sugar because it just shows the sugar molecules separating from one another. It's not even a very good video. We're not going to watch this because I don't even think it works anymore. Dissolving salt. Do we need to watch dissolving salt, or do we already know that? We know that. Thank you. And so we are now moving on to 3.1b, as in Bob. And this one we're going to zoom through super, super fast. This is on page 8. Can you recognize an ionic versus a molecular compound?
Yes.
Excellent. Can you recognize an acid?
Yes.
Can you write dissociation equations for ionic compounds and acids? Excellent. There's some examples. Feel free, if you're like, even though there were people saying yes in class, I'm not 100% sure. Feel free to do some of these just like for practice. Take a look at the answer key, and if it causes you any problems, come on in during flex or just stop by for a minute or two after class or whatever and ask me. All right. Can we all write dispersion equations? Okay. Recognizing electrolytes and non-electrolytes. Can we do that? Excellent. Blah, blah, blah. Would you be able to choose whether to write a dissociation or a dispersion for these substances? Excellent. Okay, are we done with this one? We're done with that one. Moving on to 3.1c. Again, I think this one's going to go really fast. This is on page 12. Okay. Do you know the word for that solid? What's that called? Precipitate. What kind of reaction forms a precipitate? Double replacement. And when you get a precipitate, what does it look like? The solution will look cloudy. Okay, because you have very fine particulates just suspended in the liquid. Fine solid particles suspended in the liquid. Are you able to predict the products of a double replacement reaction? Are you able to predict which of the products would be solid and which would be aqueous? That was like maybe a third of you. Are you able to, how many people would like me to go over how to predict the products? Yeah? Okay, we're going to go through this. All right, so what we would do is we would look at Na, and this is the one where we combine our outside ions and our inside ions. And remember, for our inside ions, we go backwards. And we would end up with NaNO3, and we would end up with AgCl. Those are going to be our products. Okay, combine the outside ions, combine the inside ions. At this point, you should be able to tell me which one of these is absolutely 100% for sure soluble. NaNO3. Why? Because of NO3 and Na is an alkali, and all alkalis are soluble. Beautiful. Okay, let's check on AgCl. Where would you check? Your table. So we go to our table. It is on page 3. Nope, 4. It's on page 4. Is AgCl soluble or low solubility? Low solubility. So it would be the, what's the word? The precipitate. Would you know how to write the precipitation reaction? What is happening here? Oh, I'm in the wrong one. That's why. Would you be able to write the net ionic precipitation reaction knowing that AgCl is the solid without going through the formula equation, the complete ionic equation, and then going to the net ionic equation? Could you, knowing that is the solid, write the net ionic equation just from there? Okay. Would we like to see it? Anyone? Would anyone like to see it? Yes, please. Okay. We have our solid, AgCl. That is our precipitate. And in this reaction, the precipitate is formed. So should that be the reactant or should that be the product? Product. Okay. And what two ions do we need to make that product? Ag and Cl. Okay? And that's it. Except for that it's not. You're absolutely right. It's not. What's wrong? Charges, states. Okay, so if you know who the precipitate is, you can just chuck your ions together and get that. Yes? Technically, yes, this is an equilibrium. But if we are writing a precipitation reaction, do you remember I talked about the solubility equilibrium equation? That's when we're concerned about how much is dissolving. Here we're like, this one is precipitating. So we don't care that there's going to be like a concentration of 10 to the negative 7 molar of those ions left over at the end. As far as we're concerned, this essentially goes to completion or close enough, right? Because normally when we're doing a precipitation reaction, we are doing it either qualitatively, right? Where like this precipitation occurred, or we're doing something like it would occur in a titration. And in a titration, we're looking to find out, is it 0.1 molar or is it 0.01 molar? We're not looking to say, oh, is the concentration 0.000000001 molar? Like, we're not going to those small things. So when we write a precipitation reaction, we're going to have a one-way arrow. Yeah? So this is the precipitation reaction. I'll call it the precipitation equation. Precipitation equation. The PE, precipitation equation, rather than the SEE, the solubility equilibrium equation. And where did the solid go here? The solid is on the right, and the ions are on the left. Okay, so if you're writing a precipitation reaction, it's a one-way arrow. One way. One-way arrow, solid on the right, ions on the left. Don't worry, I'm going to say this like a million times. What? You good? Okay. I am going to say this a million times. So if you're doing a titration, this is the kind. If I say, what's the precipitation reaction? You're going to do this. If you're doing anything with KSP, you're going to use the other form, which is this one. Okay? So anytime you're asked something about the KSP, also the solubility, how soluble is it, you're more concerned about the ions than the precipitate. Don't worry, I will harp on this a lot. Okay? So, okay. Could we identify the spectator ions? Could we, everybody, could we identify the spectator ions?
Yes.
Could we write the complete ionic equation?
Yes.
Excellent. Do we know what to do if we have two precipitates? Oh, okay. Is it a situation of no reaction if we have two precipitates? No, it's not no reaction because you ended up with new stuff, right? Yeah. So in this case, you would take your copper and your hydroxide, you would put those two together. You would have to make sure you'd be like, oh, do you know the charge of the copper here?
Yes, 2.
It's 2+. So you have to take that into account. If it is a transition metal, you must say what charge is that transition metal. And you'll know that because sulfate is 2-. All right, so we do our outside ions, so we'll end up with CuOH2. And then we do our inside ions, strontium, sulfate, Sr, SO4. If we look those up on our solubility chart, it turns out they are both solids. So our products would be copper hydroxide solid and strontium sulfate solid. Yes. Anything that's completely insoluble, not really. Maybe diamond. I would think that diamonds don't dissolve to any extent whatsoever. I mean, they're covalent bonds for one thing, so they're not really attracted. And carbon's a teeny tiny molecule, like it wouldn't have any London dispersion forces to speak of. Yeah. Maybe some of the other ones, like silicon dioxide, like sand, is not soluble. Yeah. Okay, so what would we know about the complete ionic and net ionic equations here? They're the same. Yes, because there's no spectator ions. Everybody gets taken out of solution. All right. What if we get no precipitate? What if both of my products are aqueous? What do we do? That is no reaction. Okay, is good? All right. We're not going to look at that. There are some, if you want more examples on how to figure out the products, you can take a look at these. If you're like, everyone was like, yes, I know how to do this, but I'm not feeling so comfortable, you could practice some of these. Okay, the answer key is there. And now we're moving on to the stuff that actually is new, qualitative analysis. This is on page 17. In qualitative analysis, we are analyzing a mystery solution. Ooh, mystery solution. So this is going to be a solution that contains one or more cation Or it could be a solution that contains one or more anion, and you'll be told what they are. So say, for example, in our first example, we have a solution that contains either calcium nitrate, which means in that, or lead nitrate, which means that we would be focused on the calcium, and we would have either that and or lead in our solution. Or we could have both, right? And what we're going to do is we're going to use precipitation to precipitate out the ions one by one. We call that process selective precipitation, okay, because we are selectively precipitating them. So what we would want is we want something. Are we going to want an anion or a cation to precipitate these ions? We want an anion. And in order to selectively precipitate them, we want something that will precipitate with calcium or lead, but not both. I know it says but not both on the next line, but I want to write it over here. Could you please go look on your table of solubilities and find something that precipitates with calcium or lead, but not both? There is more than one correct answer. Anyone got one for me? Chloride, yes. Okay, chloride would work because lead is low solubility, so it would precipitate, but calcium would fall in the all other categories. You could also, of course, if chloride is a possibility, then who else? Bromide and iodide. Did anyone find another one? Sulfide. Okay, sulfide, calcium is soluble, but lead falls in all others and is low solubility. So our possibilities then are sulfide, chloride, bromide, and iodide. I would like you guys to pick one for me. Which one do we want? Bromide? Okay. Is it possible to add bromide ions all by themselves? Can I go get a jar of bromide ions? What would happen if I tried to pack all those negative ions into a container by themselves? It would explode. So what do we need? We need a cation. So every ion that you want to add is going to need a partner. And if the partner is if this is an anion, then the partner must be a what? Cation. Now, we want a cation that isn't going to cause problems later, okay? Because we're going to be adding other things. We don't want any side reactions. So we want our cation to be unreactive. We want it to stay as a spectator ion, okay? So in other words, this cation that we choose must be always soluble. So who are always soluble cations? Alkalis. Okay, who are the alkalis? Lithium, sodium, potassium, and we're going to stop there because all the others are just like way too uncommon. If you had to pick one of these as something that you could probably find lying around in any chemistry storeroom, which one do you think is the most common to be paired up with things? Sodium. Sodium is our most common. And I would say anytime I need a cation to be the partner with an anion that I want to add, I would just always use sodium. Not that there's anything wrong with using potassium, but why complicate things, right? Always choose sodium. It's the most common. Sometimes I do have people suggest hydrogen and ammonium. Why not hydrogen and ammonium? How might they react? They can react with water. What are hydrogens? Hydrogen, something with a hydrogen is an acid. What about ammonium? Ammonium is, I got very excited and circled it in green in the last block. Ammonium is a acid. Can we guarantee that these acids will not react with other ions that are present? No, okay? So these might cause side reactions. So what do we want to use? We want to use our alkalis. Okay? Sodium being the most common. So our best option is Na+, as it is unreactive and readily available. We're almost out of time, so how much of this compound do we need to add? Well, we want to make sure that if there is lead there, that we precipitate all of it. Because anything else we add to check for calcium later will also precipitate lead. So if we don't get rid of all the lead, and then we add the thing that's supposed to show if there's calcium or not, maybe we're like, oh, I got to precipitate, there's calcium, except for it was just leftover lead. So we have to get rid of all of the lead. And in order to do that, okay, so this compound, NABR, how much do we need to add? We need to add an excess. Okay, you're not going to be able to tell me a specific amount, just say an excess. Okay, we must add an excess of NABR. And one of the things you'll have to do here is actually write out this procedure. So you would say add an excess of NABR. And then you make a statement. If a precipitate forms, lead 2 plus was present. If no precipitate forms, no lead 2 plus was present. Now we know whether there was lead or not. Now we can add something that will precipitate calcium to see if it's present. However, probably, if we did have a precipitate, this is our PBBR. What does this solution look like now? It's cloudy. If I now add something to precipitate the calcium, will I be able to tell if it gets cloudier? No. So what do I need to do before I try and precipitate the calcium? We need to get rid of the solid. Okay, so it's already cloudy with the PBBR. Can you think of a way to get rid of the solid?
Filter it.
You could filter it. Anyone got any other ideas? Anyone know what this is called? Centrifuge, yes. Okay, so what we can do is we need to remove the lead compound from the solution, and we are going to do that by one of two methods. We are going to centrifuge, which is this machine here. We put that in, and the higher density solid goes to the bottom. Yes? And we'll finish this up next day because your homework today is just to study for your quiz. I would recommend that if you have not done the very last thing on here, that you read it through. There's some Hebden questions in there as well. I will put that on Teams for you. Okay? Yes.